Good morning to everyone. So today we are going to continue our previous lecture, that is jointly Gaussian random variables. So for this jointly Gaussian random variables, so this is the basic formula of the jointly Gaussian random variable. So that is here we are going to consider two random variables. Those two random variables are nothing but x and y, and the density function is like this. So this is nothing but the density function of two random variables where x bar is nothing but the expected value of the x and y bar is going to be treated as the expected value of y. We know that this sigma x square is the variance of the x and sigma y square is the variance of y. And here in the equation we are going to observe the top row. So that is, this is nothing but the correlation coefficient, and it is going to be represented by the formula E of x bar, sorry, E of x minus x bar into y minus y bar. That is, we know what is x minus x bar. X minus x bar is nothing but the mean of x, and y minus y bar is the mean of y. So here we are going to represent the correlation coefficient like this, and this is, we know that from the basic equations. That is, if it is sigma x square, then we are going to write it for sigma x. And finally, the basic formula of this correlation coefficient rho is given by Cxy by sigma x into sigma y, and this can be represented by the following figure. So all of you observe here, we have x and y. So see, here this is nothing but y bar and this is nothing but y, and this is x and this is x bar, and the density function, that is the joint density function, is represented here, right? So here we are going to observe the joint density function of the two random variables x and y, and it should be represented like this. Okay, so the of locus of x and y is maximum at x bar and y bar. So we are going to treat these as an ellipsis. Now we would like to see what happens if this sigma x is equal to sigma y, and if the correlation coefficient is equal to 0. That is, if rho equal to 0 and both these sigma x is equal to sigma y, then the pattern is going to follow a circle. Okay, when rho equal to plus 1. So rho is nothing but the correlation coefficient, and if it is either plus 1 or minus 1, then the ellipse is going to degenerate into axis rotated by angles, and these angles are equal to pi by 4 and pi by 4. So one is towards the positive direction and the other one is towards the negative direction. That is plus pi by 4 and minus pi by 4, right? So if rho equal to 0, then the corresponding uncorrelated x and y values can be taken as by the equation, that is fx comma y of x comma y, which is equal to fx of x into fx of fy of y. So if rho equal to 0 and x and y are uncorrelated, then we are going to distribute this joint density function into marginal density functions, and this can be shown by the equation like this. So see, so this is the equation of distribution when rho equal to 0, and see here the maximum value is lies at x bar and y bar in the curve that is shown here in the coordinates. Here there is x bar and there is y bar. So here the maximum values are obtained for the given conditions, and here this is the formula of the maximum values. So that is 1 by 2 pi sigma x into sigma y into root of 1 minus rho square. And now we would like to see the marginal density functions of x and y. So they are going to be represented with the formulas. That is fx of x equal to 1 by root of 2 pi sigma x square into exponential of minus x bar whole square by 2 sigma x square. And here fy of y is equal to 1 by 2 pi sigma y square under root into exponential of y minus y bar whole square by 2 sigma y square. So these are the formulas of marginal density functions. By seeing this formula, that is, we are going to able to know that here x and y are statistically independent. So statistically independent in the sense here the joint distribution function of x and y may be divided into marginal distribution functions of fx of x and fy of y. And by seeing this equation, we are going to conclude that any uncorrelated Gaussian random variables are statistically independent, and here some results they are going to show that a coordinate rotation is by using an angle that is nothing but the linear transformation of x and y. Let's wait, I will show you the diagram of angle of rotation. So see here, so see here, so this is the angle, and here the angle is represented theta, and here the angle value is 1 by 2 tan inverse 2 rho into sigma x sigma y by sigma x square into sigma y square. And here this diagram is going to represent that the locus of constant values of the distribution function, that is density function, that is fx comma y of x comma y, and simply this is nothing but an ellipse. So here this is the formula to calculate the angle of rotation, and this is the case for only two random variables. Now we are moving to n random variables concept. Now Now let us consider the extended concept, that is in the previous one we had discussed only for two random variables. So that is nothing but that is a bivariate Gaussian random density function. And now we are extending the discussion for n variate Gaussian density function. So here n variate a Gaussian density function in the sense, let us observe here once we have x1, x2 and so on xn here. So similarly we have x1, x2 and so on xn here. So here we would like to say that if you consider n random variables up to xn, where n equal to 0, sorry, 1, 2, 3 and so on up to n, if they are said to be jointly Gaussian, then if the jointly Gaussian density function is given by the formula. అంటే అమ్మా ఇక్కడ మనం n నెంబర్ ఆఫ్ ర్యాండమ్ వేరియబుల్స్ తీసుకుంటే ఆ n నెంబర్ ఆఫ్ ర్యాండమ్ వేరియబుల్స్ అనేవి మనం x1, x2, xn వరకు తీసుకుంటాము. ఈ xn వరకు తీసుకున్న టోటల్ నంబర్ అంటే హియర్ మనం ఎంత కన్సిడర్ చేసుకుంటున్నాం, n నెంబర్ ఆఫ్ ర్యాండమ్ వేరియబుల్స్ని కన్సిడర్ చేసుకుంటున్నాం. సో n నెంబర్ని రిప్రజెంట్ చేస్తూ ఇక్కడ మనకి జాయింట్ డెన్సిటీ ఫంక్షన్ ఆఫ్ n random variables. So this can be given by this formula, right? So now we would like to see the covariance matrix for this n number of random variables. Let's wait, I will see you. So see, this is the covariance matrix of n random variables. That is Cx is equal to C11, C12 and so on, C1n. So this is the first row of the matrix and this is the first column of the matrix. And observe here we have n number of columns and n number of rows. That's why finally we are going to get Cnn. So in this matrix we are going to observe n number of random variables are there, like our rows and columns. And we have to know what is x minus x bar here. Okay. And what is this matrix that is represented with x1 minus x bar, x2 minus x2 bar and so on, xn minus xn bar. So here this is compared with the equations, that is x minus x bar whole power t, that is nothing but the transpose of the matrix. And here we would like to calculate the determinant of this Cx, and we have to calculate the inverse of this Cx also. We have to perform two operations with respect to this C of Cx, that is nothing but a covariance matrix. Now see the elements of covariance matrix. So here the elements of covariance matrix is represented like this. That is Cij is equal to expected value of xi minus xi bar and xj minus xj bar. So here I is one value and the j is the next value, right? For example, if you want to know how these are come, we would like to substitute the values, like for example, say n equal to 2, n equal to 3 or n equal to 4. So if n equal to 2, then we are going to observe a 2 by 2 matrices, that is C11, C12, C21 and C22. So if n equal to 2, we are going to get a 2 by 2 matrix with 2 columns and 2 matrices. And if n equal to 3, we are going to get 3 columns and 3 rows. So we have to represent the covariance matrix according to the value of n here. And we know that this is nothing but a variance. Okay, sigma xi square is nothing but the variance of one random variable. And see, generally we are going to represent sigma xi into sigma xj, and here we are going to use the condition that is I equal to j. Then if both are equal, then we are going to multiply those two and we are going to get this sigma xi square. And now let us observe the covariance matrix for n value is equal to 2. And see, this is the covariance matrix when n equal to 2. So this is C11, C12, C21 and C22. And we know that this is nothing but we are going to calculate the correlation coefficient value, that is rho is equal to C12 by sigma x1 and sigma x2. That is the basic formula of correlation coefficient for this two random variable case. So here our two random variables are nothing but x1 and x2. Okay, and in another way we would like to calculate the same coefficient, that is correlation coefficient, by using the formula C21 by sigma x1 into sigma x2. So these are shown here, right? So if you replace the values of C12 and C21 in this equation, so cross multiplication here we are going to get C12 value as rho into sigma x1 into sigma x2. So here also in place of C21 also we are going to get the same value. So that's why here we are representing the covariance matrix for n value is equal to 2 like this. Sigma x square is not changed, sorry, sigma x1 square is not changed and sigma x2 square is not changed, but here we are replaced the values of C12 and C21, and these values are obtained by cross multiplication of the basic definition of correlation coefficient. So these are the values. Now we would like to calculate the determinant. So we know the basic formula to calculate the determinant, that is AD minus BC. So here these are, let us consider if A equal to sigma x square and B equal to rho sigma x1 sigma x2 and C is equal to rho sigma x1 sigma x2 and D is equal to sigma x2 square. So by the basic property of determinant of a matrix, here we would like to calculate the determinant of this covariance matrix, that is shown here, the calculation of determinant, that is this is nothing but value of A and this is nothing but value of D. Okay, so AD minus B. So what is the value of B? B is nothing but rho into sigma x1 into sigma x2. And again C value is also very similar to the B. So that's why here we are going to represent with rho square into sigma x1 square into sigma x2 square. So by taking a sigma x1 and sigma x2 squares as common, we are going to get this value, that is sigma x1 square into sigma x2 square into 1 minus rho square. So now we would like to find out the inverse of this covariance matrix. Now, so this is the formula to calculate the inverse of this covariance matrix, and we know that 1 by determinant into that matrix, that is here some values are multiplied into internally to this matrix, and by solving this we are going to get our required value. So now we have to calculate that, and we have to substitute the value. if you su- if you substitute the values of x1 and x2 in a basic equation, that is basic equation is going to represent as n number of random variable. So here we are considering our n value as 2. So that's why here we are going to observe only x1 and x2 here. So if you extend this for n equal to n also, we are going to write that. That is, we had seen the basic formula of n variated Gaussian density function at the early discussion of this topic. So now simply here we are going to replace the n value with 2. ఒకసారి చూడండి అమ్మా, ఇక్కడ ఏం చేసామంటే మనం n వాల్యూ 2 తీసుకొని ఆ 2కి క్యాల్కులేట్ చేసేసి, అంటే బేసిక్గా మనం రాసిన n నెంబర్ ఆఫ్ ర్యాండమ్ వేరియబుల్స్ ఫార్ములాలో 2 వేరియబుల్స్కి మాత్రమే ఇక్కడ మనం రాస్తున్నాము. ఎందుకు అలా రాస్తున్నామంటే here we are considering the n value as 2. Okay, so if n equal to 2, what happens, that we are seeing here, and we are going to apply everything similar to n number of random variables, right? And now I would like to see you the final formula by using all these calculations. So see, so this is the formula of two random variables. So here the two random variables are x1 and x2. Okay. So first of all, we are started with n variate Gaussian density function, and for simplification, we are going to put the n value which is equal to 2, and here we had done two things. That is, we had calculated the determinant of the covariance matrix as well as inverse of the covariance matrix. After finding the inverse and determinant of the covariance matrix, simply we are going to substitute in the basic equations which are represented in matrix form, right? So this is nothing but n random variable function for a Gaussian density function, or it is also called as n variate Gaussian density function. But this final equation is going to represent only for two random variables, because while calculating we had taken the value of n equal to 2 only. So that's why observe here we have sigma x1 and sigma x2, and x1 here also we have x2. So see here sigma x1 square, and here sigma x2 square. So this is because of the consideration of the n value. So if you have n equal to 3, then you are going to get x1 bar whole square, next x2 bar whole square, next x3 bar whole square by sigma x3 square. This is the additional term, And in this second term, we are going to add here x3 minus x3 bar in the numerator, and here we have to add sigma x3. For example, if n value equal to 4, then we are going to represent up to x4 minus x4 bar by sigma x1, sigma x2, sigma x3, sigma x4. And how much the value that we are considering here for our n, that many values are going to be obtained in the equation. So see here x1 minus x1 bar whole square and x2 minus x2 bar whole square by sigma x2 square here and sigma x1 square here. So here this is for only two random variables. If we are going to extend this one, then we are going to get that many number of values of the random variables here. So this is about n random variables, and now we would like to discuss some properties of Gaussian random variables. That is, the first property of the Gaussian random variable is nothing but the Gaussian random variables are completely defined by their means, variances, and covariances. So that's why here, for understanding the n random variables, we had taken the covariance matrix, right? So this is the first property, and this is the reason why we are considered a covariance matrix in order to understand the n random variable. And the second property is nothing but if these Gaussian random variables are uncorrelated, then they are statistically independent. So here statistical independent is nothing but the joint distribution or the joint density functions are going to be separated marginally. So here the margins are nothing but if you are considering the two random variables x and y, then we know that if it is a density function, then we have to represent the marginal density function of x and y. Let's wait, I will see the marginal density functions once again. So, so see, this is nothing but the joint distribution function, and if these Gaussian random variables are uncorrelated, then they are statistically independent. So here the second property is going to prove this one. This is nothing but the property of a Gaussian random variable. So that's why in the discussion here we represented this one, even though they are uncorrelated, but they are going to exhibit statistical independence. That's why the joint density function is decomposed as marginal distribution functions of x and y. So here this is for two random variable case, and now we would like to move to the property 3. So what is the property 3 here? Here the property 3 is going to tell us about the marginal density functions, and these marginal density functions are derived from n Gaussian density function are also Gaussian, right? Are you able to understand? I am repeating once again. Listen here carefully. See, if we are considering these marginal density functions, and these marginal density functions are also derived from the Gaussian density function, are also Gaussian. That is nothing but here, this is nothing but the representation of joint Gaussian density function of two random variables x and y, and by using the property statistical independence, we had decomposed this joint density function into fx of x and fy of y. So here, this is nothing but this fx of x is also Gaussian and this fy of y is also Gaussian. So this is nothing but the third property. ఇక్కడ జస్ట్ లిజన్ హియర్ అమ్మా. అంటే ఇప్పుడు మనం ఒక n వేరియేట్ గాసియన్ డెన్సిటీ ఫంక్షన్ని తీసుకుంటే ఆ గాసియన్ డెన్సిటీ ఫంక్షన్ అనేది అన్కోరిలేట్ అయినా కానీ అది మనకి స్టాటిస్టికల్ ఇండిపెండెన్స్ని ఎగ్జిబిట్ చేస్తుంది. సో ఈ స్టాటిస్టికల్ ఇండిపెండెన్స్ని ఎగ్జిబిట్ చేసినప్పుడు ఏమవుతుంది మనకి అంటే ఎక్స్ ఫంక్షన్స్ అన్నీ కూడా ఎక్స్లోకి వచ్చేస్తాయి, వై ఫంక్షన్స్ అన్నీ కూడా వైల్లోకి వచ్చేస్తాయి. సో ఇలా వచ్చిన ఈ ఎక్స్ ఫంక్షన్ కూడా ఒక గాసియన్ ఫంక్షనే, అలాగే ఇలా వచ్చిన ఈ వై ఫంక్షన్ కూడా మనకి ఒక గాసియన్ ఫంక్షనే. ఓకే, next the fourth property, that is all conditional density functions are also Gaussian. Okay, are you able to understand this? If you place a condition, that is nothing but a conditional density. So you know how to represent conditional density. I would like to show you. Just wait. I would like to write the formula and I will show you. So see here, the condition is nothing but, for example, if you place x by, for example, y. Okay, so this is one condition, and if you place here y by x, so this is another condition, right? So this is going to represent the conditional density functions, and if you represent these conditional density functions, these are also Gaussian, whatever it may be. If it is a general or density function or conditional density function, all these functions are Gaussian functions. And finally, the last property is nothing but the linear transformations of Gaussian random variables are also Gaussian. So this is nothing but our last topic of this session. So I will clear you more about this linear transformation while we are concluding this session. So before going to start the linear transformation of Gaussian random variables, we would like to see a small problem which is regarding the rotation of axes. So now we would like to move to that problem. So see, this is the problem. That is, here we are considering two random variables x1 and y1, and these two are related to other random variables x and y. Okay, so by using the coordinate rotation, we have the values of x1 and y1 like this, right? So here the theta is going to be represented as rotation of angle. And see, here x and y we have. So this is nothing but the angle, and we decompose it into two components. That is, towards x we had written as x cos theta, and towards y sin theta. Actually, this is sin theta. This is nothing but sin theta, right? Like this. And we have to prove that if x1 and y1 are Gaussian random variables, and if these two are independent and uncorrelated, we have to show that the rotation of angle theta is equal to 1 by 2 tan inverse of 2 into rho sigma x sigma y by sigma x square minus sigma y square, right? So here we would like to prove this. So in order to prove this, we are going to use the properties of this correlation. So by using the correlation properties, if x1 and y1 are uncorrelated, then C of x1 y1 is equal to 0. So this is the property that we are going to consider here. And this is by the basic property of correlation. And we have to prove the rotation angle by using this property, that is Cx1 y1 is equal to 0. So for this we are going to use this relation, and now we would like to see how this Cx1 y1 is going to rewrite in mathematical form. So see here our two random variables are x1 and y1, and here the correlation of x1 y1 is equal to expected value of x1 minus x1 bar into y1 minus y1 bar, right? So we know the values of x1 and y1 here. So here the value of x1 is nothing but x cos theta plus y sin theta, and the y1 value we are going to substitute here y cos theta minus x sin theta, so which is given in the problem. So this is given in the problem, and we have to substitute here. So in place of x1 directly we are going to represent with x cos theta plus y sin theta, and in place of y1 we have to replace y cos theta minus x sin theta. But what about this x1 bar? So if x equal to if x1 equal to x cos theta plus y sin theta, then x bar is going to represented as x cos theta plus y sin theta whole bar. Now I would like to uh, see you that calculation. Just wait. So see, now I had substituted the values of x1 and y1. So this is the value of x1, and this is the value of x1 bar, and this is the value of y1, and this is the value of y1 bar. So if you simplify these values, so simply apply minus to this one and apply whole bar initially here. Then we have x bar cos theta and y bar sin theta here. So after applying the bar here, let us apply the minus symbol towards this. Then we are going to get minus x bar cos theta minus y bar sin theta. So in the similar fashion, if you apply this one also, here we are going to get minus y bar cos theta. Here we have minus and here we have minus. So that's why here we are going to get plus here. So minus into minus, we are going to plus here. That's why here plus x bar sin theta. And if you take common, so now observe the term. Here we have x cos theta and here we have x bar cos theta. So let us take cos theta as common. Then we are going to get this value, right? So in the similar fashion, we have sin theta also here from here. Y bar, right? That is sin theta. So in the similar fashion, if you take out the common values from this second term also, we are going to get this one. And now we have to see this term, how this term is going to appear. Just observe this one carefully. This is nothing but multiplication. This is nothing but a multiplication. So if you multiply this term with this term, you are going to get cos square theta. And in the similar fashion, if you multiply this one with this function, then you are going to get a sine square theta here. Okay. If you multiply this one with the first we are going to get a cos square theta, and if you multiply this second term with this second term, you are going to get a sine square theta. And we have to multiply again here with this one too, this one. Okay, so that can be represented in the equation, right? So x minus, sorry, so this is cos square theta, this is sin square theta, again cos theta into sin theta. That is, this is the multiplication. X minus x bar into cos theta into x minus x bar into sin theta, right? So x minus x bar into x minus x bar. So we are going to get x minus x bar whole square into cos theta sin theta. Okay. So in the similar fashion, here also we have y minus y bar cos theta and y minus y bar sin theta. So here these are the two terms which are response to y minus y bar whole square sin theta cos theta and x minus x bar whole square cos theta sin theta, right? So now the further equation is nothing but taking commons, taking commons and simplify these ones. So see here in the terms we have sin square theta, cos square theta, but we have the common terms x minus x bar into y minus y bar, y minus y bar into x minus x bar. So take out these two words as common, then we are going to get this term. that is x minus x bar into y minus y bar into cos square theta minus sin square theta, right? And now here we are representing this sin theta into cos theta, that is sin 2 theta by 2. So this is the trigonometric relation, and by using this trigonometric relation, here we are going to replace this sin 2 theta cos theta by sin 2 theta by 2. So that's why here we are going to get this value. And again, if you observe this equation of cos square theta minus sin square theta, this is nothing but the value of cos 2 theta. That's why here we are representing the cos square theta minus sin square theta by using cos theta. Or in other words, we are going to say that cos square theta minus sin square theta is equal to cos 2 theta, right? So that's why in this term it is reformed into cos 2 theta. Again, here there is a common term is there, that is what is the common term here? 1 by 2 sin theta and 1 by 2 sin theta. So if you take 1 by 2 and sin 2 theta as common, then the remaining terms are nothing but e of y minus y bar whole square and e of x minus x bar whole square. So that's why here we written like this. But by using the basic formula, we know that the correlation of x and y, that is e of x minus x bar into y minus y bar, and the correlation coefficient is equal to this one, that is rho is equal to cxy by sigma x into sigma y. And if you apply the cross multiplication, then we are going to get the value, that is cxy is equal to rho into sigma x sigma y, right? So now we are going to see what happened if you substitute these values. So see here, so this is nothing but the sigma x square value, and this is nothing but the sigma y square value. And we would like to see the correlation, and the basic correlation function is represented like this. So see here, cx1y1 is equal to cxy into cos 2 theta plus 1 by 2 into sin 2 theta into sigma y square into sigma x square. So that is nothing but in the previous equation we have 1 by 2 into e of y minus y square minus e of x minus x bar whole square into sin 2 theta, that we are going to represent with their original values. And we know that because expected value of x minus x bar whole square, which is equal to sigma x square, and expected value of y minus y bar whole square is equal to sigma y square. సో ఇక్కడ వచ్చిన మనకి ఈ బేసిక్ ఈక్వేషన్స్ ఏం చేస్తున్నాం అంటేనమ్మా, ఆ పైన ఉన్న 1/2 సైన్ 2 తీటా ముందు ఇక్కడ మనకి ఏదైతే ఈ మల్టిప్లైడ్ వాల్యూస్ ఉన్నాయో మనకి సిగ్మా వై స్క్వేర్ సిగ్మా ఎక్స్ స్క్వేర్తో ఈక్వల్ అవుతాయి, కాబట్టి మనం వాటిని ఇక్కడ ఇలా రీప్లేస్ చేసామమ్మా. సో ఇక్కడ మీరు అబ్జర్వ్ చేస్తే ఈ సిగ్మా వై స్క్వేర్ వాల్యూ ఏమొస్తుంది మనకి, ఎక్స్పెక్టెడ్ వాల్యూ ఆఫ్ వై మైనస్ వై బార్ హోల్ స్క్వేర్ కదా, అలాగే ఇక్కడ expected value of x minus x bar whole square, right? And by using the basic property, that is starting lo cheppamma emani sigma cx1 y1 is equal to 0. So this is nothing but a property. So now we have to equate this one to 0. We have to equate this one to 0, and if you equate this RHS to the 0, and by simplifying we are going to get our required value, and I would like to show you the final result. So that is tan 2 theta is equal to 2 rho sigma x sigma y by sigma x square minus a sigma y square. So if you um, or if you want to find out the theta value, you have to follow the procedure. That is, first of all, we have to keep 2 theta on LHS, and if you send this tan towards this, then we are going to get tan inverse, right? That is the tan inverse of 2 rho sigma x sigma y by sigma x square minus sigma y square, and then we need to find out only theta but not 2 theta. So that's why here this is nothing but a multiplication. Then if you move that towards the RHS, then it will becomes as 1 by 2, and this is going to give the formula, and which is our required formula, that is our final formula. So this is our final formula, and hence it is proved. So this is the solution of the problem, and now we are moving to transformation of random variables. So now let us see the transformation of random variable. So in the second unit, we had discussed about transformation of only one random variable, and now we are going to see the transformation of two random variables or a more number of random variables. So that is, if we are extending this discussion up to n number of random variables, then we are going to represent the term n like this, yn. So here yn stands for, we are going to consider n number of random variables. And let us consider n number of random variables, whether they are continuous random variables or discrete random variables or mixed random variables. That's not a matter. But the transformation here is represented with this Tn. So observe here, we have x1, x2 and so on xn. So this is going to represent as the n number of random variables, and here our n value started from 1 and so on up to n. And we have to consider the type of transformation also here. That is, if this transformation may be a linear transformation or non-linear transformation or continuous transformation or segmented transformation. For example, now we are assuming that these random variables are produced by a single valued continuous functions. అంటే ఇక్కడ ఒకసారి చూడమ్మా, ఈ yn అనేది మనకి ఒకే ఒక ఫంక్షన్ ద్వారా జనరేట్ అయితే, ఓకే, and here this Tn is nothing but continuous partial derivatives. Partial derivative in the sense dou by. Partial derivative is going to be represented with dou, right? Then we need to take a set of inverse. That is, this equation is going to represent with y, that is yn is equal to Tn of xs here. X values are lies here. So if you want to know these x values, what we have to do? We have to inverse this. Just wait. I would like to see you that equation also. So see. So all of you see here. So in the previous equation, we had seen for yn is equal to Tn of x1, x2 and so on, xn. But here, this is the another representation, xm, for the same consideration, Tm. So this is nothing but inverse, and that is nothing but the direct one, right? So observe here, which is very similar to our previous unit transformation. So if you have your notes, please check with your transformation of random variable concept. So there we are going to observe for only one random variable, and here this is nothing but the transformation of multiple random variables. So here multiple in the sense we are going to consider these up to n number of random variables. And let us consider a sample space, and if this sample space is going to be exhibit one-to-one correspondence, so there is no need to discuss about once again the one-to-one correspondence in the sample space. You know that very well, and you have learned from your previous classes, I think, right? So let's continue our discussion professionally, right? So see here we have x and y, and let us consider if Rx and Ry are the closed regions of the random variables x and y, then how the joint probability density functions are shown. So this is shown by a region. Let's wait, I will show you the diagram. So see, this is the nothing but regions of x1 and x2 plane. That's why simply here we are considering again for two variables or two events in the sample space like x1 and x2. We have n number of events in this sample space, right? So this is the diagrammatical representation that is see here. So this is the region, okay? This is the region that is 0 less than x1 less than or equal to yx2, right? And below this one, that is x1 is equal to yx2. So this is nothing but yx2, and this is the required region, all right? Now we would like to see the mathematical representation. So see here Rx is nothing but closed region of x, and Ry is nothing but closed region of y. So both are equal to each other, and we are extend this discussion to a number of random variables, that is x1, x2, xn, and so on, dx1, dx2, up to dxn. So in the similar fashion, here also dyn, right? So this is the basic formula, and if you apply the transformation, what happens? Let's see now again by using the formula. So see, so if this is the closed region of x, and what about the transformation? Now see here the transformation, that is x1 is equal to t1 inverse of y1. Actually this is t1 inverse of y1, and here x2 is equal to t2 inverse of y2, and so on. Xn is equal to tn inverse of yn. So see dy1, dy2, and so on dyn, right? So here we have a term called this mod j. So what is mod j here? So mod j is the magnitude of the Jacobian. Okay, magnitude of the Jacobian j of the transformation, right? And here this Jacobian is nothing but determinant of a matrix of derivatives defined by the partial derivatives. As we had previously told that this is nothing but some partial derivatives. That is, if the closed regions of Rx and Ry are represented with the random variables x and y, then the joint probability density function are given by the partial derivative equations. Just wait, I will show the Jacobian determinant matrix. Just wait. Okay, so see here, this is nothing but the representation of the determinant of a matrix of derivatives defined by Jacobian. That is dot E1 inverse, okay, dot E1 inverse by, now observe here, which is very similar to our covariance matrix as we had discussed previously in this session, which is very similar to that one. And we would like to see, and we have to conclude how this we are going to apply to our equation, right? Just wait, I will going to see you the mathematical. Okay, so see this one, this is nothing but the formula, and here Ry is going to represent the closed region of y, and again here also we are going to observe Ry. So this Ry is nothing but the transformation. That is, what is the difference here? Here we are going to take a direct y values, but here we are going to represent with this x1 is equal to t1 inverse of y1, x2 is equal to t2 inverse of y2. So that is the only difference, and this is nothing but the determinant of Jacobian matrix. And just now we had seen how the structure of the Jacobian determinant is there. And if you remove the integrals on both sides, if you remove the integrals on both sides, then we are going to get the a final equation of this transformation. Just wait, I will show you, right? So see here, so this is nothing but the final formula for the transformation of n random variables. So which is very similar to our second unit general transformation. చూడండి ఒకసారి, ఇప్పుడు y1 y2 and so on yn తీసుకున్నాము. సేమ్ వైని ఎలా రాసుకుంటున్నాం మనం? సింపుల్గా y ఈక్వల్ టు టీ ఆఫ్ ఎక్స్ కదా. సో టీ ఆఫ్ ఎక్స్ అంటే అప్పుడు మనకి ఎక్స్ కావాలంటే ఏం రాసుకుంటామమ్మా? టీ ఇన్వర్స్ ఆఫ్ వైగా రాసుకుంటాం, right? So this is the logic behind writing this, except adding of this Jacobian matrix, right? So with this we had completed the transformation of multiple random variables. So this is comes under transformation of multiple random variables, and we would like to see two considerations, are they can be treated as node points. I will show you the first node point which I had right now told you. That is the basic formula of a single random variable transformation. Just wait, I will show you. Okay, so see this formula for this single random variable transformation. We had y equal to t of x and x equal to t inverse of y. Okay, so if you know the density function for this one, then it will become fi of y is equal to fx of x equal to t inverse of y. We have to represent like that. Just wait, I will show the formula. Okay, so see, fy of y equal to fx of this one is nothing but the transformation. As we had previously said that if y equal to t of x, then x equal to t inverse of y. So here we have to put this y value, right? So in the similar fashion, this is nothing but the determinant. That is mod dt inverse t1 inverse, right? Fy of y equal to, this is nothing but fx of x into, this is nothing but dx by dy, right? So this is the node point 1, and here the node point 2 is nothing but the similar equation. If we extend to two random variables, what happens? What happens in the sense, there is a small change in the determinant, that is Jacobian determinant. Just wait, I will show you the equation. So see, so this is the case of two random variables, and this is the joint density function of the two random variables y1 and y2. Okay, so see, this is the only variation for two random variable transformation. So here, if n equal to 2, we are going to consider here y1, y1 and y2 in terms of y, x1 and x2 in terms of x. So this is the only variation, and observe the determinant here. So with this, we had completed the transformation of random variables, and now we are moving to linear transformation of a random variables. Okay. So if we are going to um, perform the linear transformation of a Gaussian random variable, then what happens? First of all, we have to know what happens if you perform linear transformation to a Gaussian random variable. What happens? If you apply linear transformation to any Gaussian random variable, whether it may be a single random variable or two random variable case, or it is unvariate random variable case also, we are getting the same one, which is also mentioned in our properties of Gaussian random variables. That is the last property of the Gaussian random variable is going to tell us that the linear transformations of Gaussian random variables are also linear. So now we are going to prove that. Just wait, I will show the basic mathematical representation of Gaussian random variable. So now consider here, if you consider n Gaussian random variables, that is represented with yn, and if all these transformations are linear transformations, then we are going to represent the variable 1 like this. That is a11 into x1 plus a12 into x2 plus and so on a1n into xn. This is nothing but the first row representation, and this is nothing but the second row representation. So if you get a clarity when you observe the matrix structure of this transformation, so before going to see the